Hey everyone, this is LegoMaster99 back at you guys again with another video. Today you can see I am in the Redstone Computer 5.0 world again after quite a long time. In this video I would like to explain how this computer works, do a breakdown of the computer. This is sorely overdue. I should have done this a few years ago, but now that we're getting back into things, I thought that this would be a great place to start with getting back into content. So the way we're going to break down how this mess of wires and stuff works will be a little bit different from the previous breakdown videos that I've put together for my Redstone computers. Because of the multi-core nature of this computer, there are four, separate compute units, one for each core. And so I would like to start by breaking down and explaining how each core works independently. And then once we have learned about how that works and how it's all put together, we're going to discuss a little more about how they are connected to each other, and then discuss some of the peripherals that are connected to the computer, the plotter, the displays here, the various registers, parallel port or serial ports. I'm thinking of older Redstone computers there. And then finally, we will talk about some of the other differences with this computer compared to the other ones. This will be a little more of a technical dive into how this computer was put together. Without further ado, let's jump right into the single core explanation. So we are here at one of the cores of the computer, and all four cores of the computer are exactly the same. They are identical, so we can go ahead and explore how one of them works, and then that's how the rest of them work. So to start off, all the cores are in an off state, so nothing is happening. When one of the cores gets turned on, either by turning the computer on up at the input panel or by using the core on or core off instructions, the core will be turned on by this line right here, and this is just a command block that says core 3 init. The core being on will allow us to read the instruction at address 0 of the program memory. So like I mentioned in the showcase video for this computer, there are 128 lines. I called them lines back then, but there are 128 different addresses for instructions, so this program memory can store 128 instructions. To read that, we have the decoder here. This is a full 7-bit decoder here. So we will take 7 bits, and this allows us to have 128 outputs from 7 inputs. And this input for the decoder is read from the program counter, which is this register in green here. All registers are green in this computer. And so when the core turns on, this is initialized to 0, and we read the instruction at address 0. And so once we have an address to read, address 0 to 127 for 128 total addresses. Once we have an address of an instruction to read, that decoder will allow us to read that instruction, and the various bits of the instruction word will be output on this central, bus right here. This isn't really a bus, but it's a central area. And so you can see here that each instruction is split up into different sections. We have like this magenta section, purple section, gray, red, green. This is like a light blue, dark blue. Or I guess this is a teal, blue, dark blue, and then gray, or dark gray. So there's different sections for different parts of the instruction word, and they have different purposes. And so now I'll go ahead and explain what each one of those is and what it does. These first 14 bits of the instruction word are for branching. It allows the core to select the next address to load into the program memory to fetch the next instruction. These first 7 bits here are the address of the next instruction to load when a particular condition is false or the default. And then these next 7 bits here contains the address for the instruction to load if a particular condition is true. In the showcase videos, or in times past, I would call this the go-to false and go-to true, and then this would be the go-to circuit. I'm trying to use a little more proper terminology so that it's a little less, me making up my own words. So these 2 addresses are inputs to a 2-to-1 multiplexer. So we have the 2 inputs to the multiplexer here, and then the single output on this side. The input that is multiplexed to the output is dependent on the output of the conditional circuit, which we will look at when we talk about opcodes and whatnot. This is the output from the conditional circuit here, and this indicates whether a particular condition is true or false. So you can see now that the wire is low, and we are selecting the address in this portion of the instruction word. Conversely, if the y was high, meaning the condition was true, we would pick the address encoded in this portion of the instruction word as well. And this output will be the final address of the next instruction to load on the next cycle. That goes to the program counter. And so every cycle, which is a little clock, right? Every cycle we will update the program counter with the next address for the next instruction to load. So that's how we step through different instructions in a program. All right, so I'm going to skip over this gray section for a second and jump over to the red section. This red section of the instruction word is the opcode, is where the opcode is encoded. And so the opcode is basically what operation the instruction is going to perform. There are numerous opcodes that this computer supports, and for all of these opcodes, they either take 0, 1, or 2 inputs. The first input is denoted throughout the computer literature and documentation as input A, and the second input is denoted as input B. For these opcodes, there are 2 modes here. We can see mode 2 up here and mode 1 down here, but we will start off with mode number 1. For mode 1 here, we have a variety of instructions, including an add, subtract, compare, which will simply do a comparison operation between inputs A and B and no additional logic. We have shifting instructions, so a bit shift left, a bit shift right, and then all of the bitwise operators that you can do on 2 inputs. We have not, XOR, XNOR, AND, OR, and NOR. And then we have 4 GPU opcodes here. I call them GPU opcodes, but they are really for the plotter. So this opcode here is the GPU encode point, and this will take 2 1-byte numbers and compress them into a single 1-byte coordinate point that can be drawn on the plotter. We have the GPU draw instruction, which will take a coordinate encoded in this encoding scheme provided by this instruction and draw that on the screen. The erase point will do the exact same, but erase a point. And then this opcode will enable use of the GPU Granular unit, which allows you to send massive amounts of data to the screen in a very efficient manner, and we will talk more about that when we discuss the plotter. For the second mode of opcodes, we have the test opcode, which we will talk about in a little bit. We have the core on instruction, which will programmatically enable a core. We have the core off instruction, which will programmatically disable a core. And then we have the GPU clear opcode, which will clear the screen up there. In particular, I want to point out this instruction, the test instruction, to you guys. This instruction is the core's branching instruction. And so what this will do is when we have an instruction with this opcode, it will evaluate a condition and then jump to a different part of the program, depending on whether that condition is true or false. And so this test opcode takes advantage of what we talked about previously here, as well as these 4 bits that I skipped over. These 4 bits here are the extension bits to the opcode that is provided in the opcode section of the instruction word, and these extension bits have 2 purposes. The first purpose is to pick a condition to evaluate when using the test instruction, the test opcode. The second purpose of the extension bits is to pick which core to programmatically enable or disable via the core on or core off opcodes. Now, relating to the test instruction that we were talking about, we can encode 16 different conditions here to branch on, and these conditions are dictated right here. So we have a carry out from the ALU condition. We have a variety of logical conditions from the ALU, such as B equals 0, B is greater than A is equal to B, A is equal to 0, A is greater than B, A is greater than or equal to B, B is greater than or equal to A. And then we have other conditions from other sources around the computer. For example, these 4 conditions here are from the user input panel when you push a button on the control panel. And then this condition here is a data received condition. So this condition will be true when we have data that is stored in the cache of the serial input port. We have a stack overflow condition here, which will be true when the hardware stack has overflowed and it cannot store any more data. And then we have this data stream active condition here, which I will mention now because I'll probably forget to explain it later. Effectively, this was my attempt for to mitigate bus contention for the multi-core, what do you call it? The multi-core system, since there is a single main bus, I lost the sign, a single main bus where all the data is routed onto, which we will see later. This condition will be high when there is data on the I call it the master output bus, the main output bus, basically the bus that connects all the outputs of the cores together to RAM and all that stuff. If this is low, we would be safe to push data onto the bus, and if it was high, we would have to loop and wait for this to go low before it was safe to put data on the bus without, to avoid data corruption and things like that in a multi-core environment. And so once a condition is selected, and the condition is true, this black wire will go high. And with that, that is how the entire branching system in the computer works. It is a combination of the test opcode, the 4 extension bits to pick which condition to evaluate, to branch on, the conditional circuit here, which will evaluate whether that condition is true. And based on the result of that circuit, we pick which instruction to jump to next. All right, to continue our explanation of the various pieces of our instruction word here, I'm going to skip these bits for now because it'll make a little more sense to introduce them back later. At this point, we have effectively described where the program is going to jump to next and what operation the current instruction is to be, what type of instruction it is. Now, for all instructions, we need 2 things. 1, you got to tell the computer what to do. And then 2, you got to tell the computer what data to do that thing on, right? Or what data to use. And so that is the purpose of this portion of the instruction word here, which is broken up into 3 pieces that I will explain now. Now, this computer's instruction set allows us to encode 2 different portions of data in this lighter blue and darker blue sections. And then it also allows us to encode an immediate value here in this gray section. And so this immediate value will effectively be any constants or any constant data. For example, just to make it concrete, if we were to take any user input and add 5, that constant 5 would be what would be encoded in this immediate area here. And so the reason why I called these 2 portions of the instruction word data sources is because they can be configured in a variety of different ways depending on a few flags that are set, some of which are in this section that I skipped over. The default configuration for these 2 data sources here is such that this lighter blue area is to act as the place where you would encode the data source for the instruction to read data from, so the read section. And then this darker blue section would be where you would encode the portion of memory or area on the computer where you would want to write the output of the instruction to, where you want to write the result to. And so for this default configuration, we are reading from memory. We are reading from the system RAM. And since that has 31 bytes, I believe, of accessible memory, we have 5 bits here, 1, 2, 3, 4, 5, to read all 31 bytes of that RAM. And then same thing here for the write. These 5 bits here will determine which address in RAM to write the result of the instruction to. Now, it is important at this point to mention that in this design, for this Redstone computer, there are 3 different data sources, excluding whatever comes from the user control panel. There is the system memory, there is the onboard cache for the core, and in this case, for this core, and in every core, it'll be right next to the ALU, which is this thing right here. This is the system cache. And then also the registers. There's a variety of read-write registers that you can take advantage of that are special in this computer that I will talk about in a few minutes as well. And so to choose between the RAM or the cache data source, we have this flag here. It'll be this bit for the read section and this bit for the write section of the data source to determine whether you want to read or write to either the cache or the RAM. Now, to interact with the special registers that are in this computer, we need to take a look at the select bits that I skipped before. In particular, I want to emphasize these 2 bits first. So this bit here will toggle the read data source to read either from an address, which is either cache or RAM, or a register. And then this bit does the exact same purpose, except it's for the write data source in this dark blue area here. Now, the registers that you can read and write from are specified in a decoder here in this portion of the core. And so these registers that are labeled are ones you can read from using the read data source. So we have the core status register. We have the go-to register, which is the program counter. The data port register, so this is the serial input port if you want to read data from there. The user input register from the control panel. The random number generator register, which is a register where you can read random data from, and then the global stack if you want to read from the stack. Now, we also have registers that you can write to, And these registers are labeled here. Again, the core status register, the program counter register, the serial output port, if you want to write to that, or the serial port, the decimal display, and the I/O output register. And this register is connected to the visual outputs in the control panel. The GPU point register, if you want to write data to the GPU. The GPU granular register, which we'll talk about later. And then the global stack if you want to write to the stack, if you want to push a value onto the stack. Now, related to encoding data sources in your instruction, there is a third bit here, the DR toggle, which stands for dual read toggle, which will change how these two data sources are interpreted, which is why I called them data sources and not strictly the read data source and the write data source. When this DR toggle bit is high, that select bit is high, the write data source instead becomes a second read data source. So that DR toggle will be very useful for when you have instructions that require two inputs, which turns out to be a majority of the ALU opcodes. And in that case, the primary read here will act as input A, and then the secondary read data source here will act as input B. To finish off our discussion about the various portions of the instruction word, let's go ahead and talk about the last few bits here. So this mode bit is pretty easy. This will allow us to pick which ALU opcode, core opcode mode to pick from that we talked about earlier. And then these two bits here are related to a concept that I call forwarding. And effectively the premise is this. Imagine you have a bunch of nested ALU operations where you want to run them as fast as possible. Traditionally, what you would do is that for each instruction, you would read from a memory source, perform an operation, and then write the result back to another memory source. And then on the next instruction, you would read from that, maybe a different memory source, and so on and so forth. However, memory reads and writes are very expensive, especially when you have hardware that is this big and you have to make a very long round trip. So let's take a look here. We have all of our core logic happening here, and the global RAM, or the system memory, is all the way over there. So it physically takes some time for the data to travel across the main output bus, which is here in white, to get over to RAM and all these other memory sources and whatnot. And so the concept of forwarding in this architecture's case is a way to optimize that loop and to cut out these extraneous memory reads and writes that might be tedious. And so a combination of these bits will turn on various pieces of forwarding hardware. And a really good example of forwarding is effectively forwarding the output from the ALU straight back into the input of itself. And so you can see that this will allow for nested operations to occur very quickly and efficiently. And so that is the most common use of these two bits here, the forwarding mode and the forwarding toggle, that you will see used with this computer. But there are a couple other special pieces of forwarding hardware that are implemented that you can enable with these bits as well to enable that sort of optimization and reduction of memory trips in this computer. All right, so now that we've broken down what each component of the instruction word actually does and how it's encoded, let's go ahead and jump over to the ALU. So the ALU is the arithmetic logic unit, and this is basically the brains of the core that does all the math operations and all that stuff. What happens is that for each instruction, we fetch it from the program memory. We decode it using the decoders and various hardware that we explained earlier for these different parts of the instruction word. And then we have an execute step where we perform the instruction that's requested. A vast majority of the time, this is either using the ALU or moving data from one place to another place. So this orange circuit, or collection of circuits, let's see if I can get a better view of it down here. So this is another core. This is the bottom of the core. So this here and that, this makes up the ALU. And so the ALU has two inputs. We have input A, which is this register at the top here, and input B, which is this register at the bottom. Like I mentioned earlier, the ALU here is actually a collection of circuits, and we can break them down into four major components. We have the adder unit, we have the comparator, the bit shifter, and then we have the bitwise operator circuit. So the way these circuits are used is that we take copies of the inputs. We have input A and input B, and they are all split off to the 4 different circuits that I mentioned. And so let's go take a look at those now. So this is all busing here. So this is the adder. This is proper English's 4-tick. I think it's a carry look-ahead adder. I don't remember the exact specs because it was from a few years ago. But this is an adder, and then in front of it is a little subtractor unit that I built in because binary subtraction actually uses 2's complement. And so this circuit will effectively do 2's complement in one go. So that's the adder circuit here. And then we also have a copy of inputs A and B coming over here to the comparator. So this here is the comparator circuit within the ALU. We have 4 outputs here from the comparator circuit. We have A equals 0, A equals B, B is greater than A, and where's the last one? Here we go, B equals 0. So these are the 4 core comparisons that we have, and then the remainder of the comparisons are derived from those. And then over here we have the bit shifter. This is a very simple bit shifter. We see we're just taking inputs and just shifting them to the right. This is a right shift, I believe. And then we have the left shift on the bottom. So that is the bit shifting circuit here. And then in the very back here we have the bitwise operator circuit, which is responsible for all of the bitwise operators that the ALU can perform. And so we create or we generate outputs from each one of these circuits simultaneously whenever we have inputs being passed into inputs A and B to the ALU to perform a calculation. And so for an example, the ALU output is output on this gray bus right here. The bitwise operator outputs come off on this bus right here. And then we have the bit shifter outputs coming off on this bus right here. And so these 3 outputs from these 3 circuits are multiplexed together and combined from those 3 outputs into a single output bus right here for the ALU. And then for the comparison circuit here, or for the comparator, I suppose I should call it a comparator, these signals are sent up to the control and status register, the CSR for the core. Let's see. Up here. And so that is how the logical conditions get updated. They get updated through this register, which is sourced from the comparator within the ALU right here. And so which ALU circuit actually gets pushed onto this output bus for the entire ALU is dependent on the ALU operation. So if we were doing an add or subtract operation, we would pick the output from the adder circuit over here. If we were doing any bitwise operators, we would pick the output over here. And then if we were doing any bit shifting operations, we would pick the output that was generated on this side. And then once all of the computation has completed, it will be saved to the ALU output register, which is right here. All right, so the output from the ALU is sent to 2 places once it is computed. The first place is the main output bus, which all other cores are connected to, and it's the main bus that goes to and from the peripherals and RAM and all that stuff. And that is this white extension here. So once we get here, this folds over. If we follow the white bus here, this connects to the main output bus, which is right here. The other place the ALU output goes to once it is computed is to the onboard cache. And so that is this bus here. It gets broken up and sent down here. This is the input to the 8-byte dual read single write cache right here. And so these 2 buses, the one that goes to the cache and the one that goes to the main output bus, are what make up the write back portion of the instruction cycle. So at the end of every instruction, something has to be written back to memory somehow, and that's what does it. And so that is a relatively detailed breakdown of how a single core in this computer works. So we do essentially for each instruction, we do the fetch, decode, execute, write back cycle over and over and over again for each instruction, and that's how the programs are able to keep their state and make progress. Now I want to point out some circuits for the core that are not a particular part of that fetch, decode, execute, write back cycle. And one of them here is this circuit. This is the circuit that allows the user and the program as well to control the speed of the core. So we have the different speeds here all set up in their little repeaters. So only one of these will be active at a time, sending the clock to the core to update its state. So the way this works is we have a 3-bit, 3-bit speed register. And this encodes 8 possible values for speed. And what will happen is this is either set by the user or the program. And this will select a particular speed to run the core at. And this line right here is the clock line, the main clock line. And this goes into the program counter register right here to update the next instruction to execute. And I believe that's the only place the clock line goes to. Yeah, so in other designs of processors, the clock line goes to various other portions to keep things synchronized. But in the Redstone Computer 5.0, the only synchronization needed is to update the program counter. So every clock cycle, the program counter is updated for the next instruction to process. Alrighty, so with that, our discussion about how a single core works on this computer has completed. We have talked about all the different components of the instruction word, the various process of how instructions are fetched, decoded, executed, and then how their state was persisted via the write-back system, or the write-back step in our instruction cycle. And now we are going to talk about how these cores play into the larger picture of how the computer works as a whole. So I think a good way to go about this is to really talk about how these cores are connected to each other, and then how the cores are connected to the different peripherals and devices and various registers and stuff that are connected to the computer that we see right here. So to do this, we will start at the enhanced RAM. I called it enhanced RAM, but it's effectively 31 bytes of memory that is shared across all 4 cores. Just like with the cache on each one of the cores, this memory is dual read, single write, and those inputs come from each one of the various cores. So this pink circuit here is a combination of decoders and just busing. So here are some buses, and then we have decoders on this side. And then we have inputs on the front of the RAM right here. These 2 stone slab towers are the inputs for which addresses to read or write. And that gets followed up here on these 3 pink buses. And so we have here, this bus here is the input to the write, so which address to write to in memory. This is read number 1 and then read number 2. All of these buses are then connected to the various cores. We follow that over here. That gets split off here. So then we are connected back to our data source 1 and 2 inputs over here that we discussed earlier. And then we have more buses that go over to the other core for the same function. And then yet more buses for those reads and writes that go to the other 2 cores as well. Let's see if we can find that. Yes, we have one here, and then another one right here. And then I believe it'll be easier to talk about the output of the RAM first. So if we think about reading from RAM, this data comes out on this dark gray bus and gets propagated onto this white bus here, which is the main input bus or master input bus. And so this bus is propagated through the entire computer and sent to all of the various inputs. That's why it's called the main input bus. So you see here we have some inputs flowing over to, let's see. Yeah, the main input bus is connected to the ALU input on each core. So this white section here that branches off, it's connected here. And that's connected to each core. So if we look down here, here is also a section of the main input bus. Let's see. The main input bus is down here. And there's 2 portions of it, one for input A and input B for each core. And then once that data gets fed into each one of the cores, it does all of its logic through the ALU and whatnot. And then the output is pushed onto the main output bus, which is this upper portion here in white as well. And the main output bus connects all outputs from each core all the way back to memory right here, and also to a variety of different registers and peripherals. So this concept of the main input bus and the main output bus allow data to flow from memory to any portion of the computer for input, and then data comes out on any core or any peripheral on the main output bus, and then that can be made accessible to other portions of the computer. So the main input and main output buses are really what connect every portion of the computer together into a single interface that can be accessed by any core or any peripheral. All right, so now let's talk about these peripherals I've been mentioning. So all of these peripherals are connected via the main output bus and the main input bus. And whether a particular peripheral or device is connected to the main input bus or main output bus, or actually both, depends on the register system here that we looked at when we were talking about which registers we can read to and write to. So for example, the data port register, the user input register, RNG, and the global stack are all connected to the main input bus. And then all of these other devices here, the decimal display, the data port again, raw binary display, I/O output, GPU registers, and the stack are also connected to the main output bus. So let's take a look at the peripherals that are connected to the main input bus first. So that is this portion of the peripheral stack over here. And starting off, we have input from the serial input port. So we send a serial signal through here, and then this will get decoded and stored in this register right here. And then when we select reading from the serial port, that will get pushed onto the main input bus through this interface right here. And then the next peripheral is right below it. This is the random number generator. When we read from this, it'll generate a random number and then output that here to the main input bus. The next peripheral is the stack. So this bus gets wrapped around from the output of the stack, or the top of the stack supposedly. So when we read, we actually are doing a pop operation, and that value will get popped from the stack onto here and then pushed onto the main input bus through this interface. And then the last input we have is the user input from the control panel. So all of the buttons will get, all of their inputs will be propagated through this bus from the control panel and then gated through here to get onto the main input bus. All right, so now let's take a look at the peripherals that are connected to the main output bus in the peripheral stack. So that is this portion over here in the computer. So starting from the top, we have the decimal display register right here. So when we select to output data to this location, that data will come up from the main output bus through this set of wires right here, and then get gated and get written to this register. And then this propagates up to a binary to BCD decoder, which is right here. And then after the BCD conversion step, we do another conversion again from BCD to 7 segment. And then all of those 7 segment outputs get displayed on the 7 segment screen right here. The next peripheral we can output data to is the raw binary display. So it's exactly the same as the decimal display, except we have a dedicated register for it here, and that value gets pushed straight onto the display as so. The next output we have is the serial output port. So the data gets saved into this 1-byte register and then serialized through this line, and then gets output to the serial output port here. The next output we have is to the I/O output panel on the control panel, so that red output panel right there. You notice that we do not have a register here, and that is because if we did, it would make this raw binary display redundant. So this is meant for more of transient signals, such as flashing lights or things like that, versus a more persistent output, such as something you would put on the raw binary display. That output gets gated through here from the main output bus and then pushed straight over to the output through this red bus right here. The next location we have, or the next peripheral, is the stack. So this is where if you want to push a value onto the stack, this is where it'll come from the main output bus, gated through this gate right here. And then if I can get through, it'll get pushed onto this gray bus. Ooh, it's a maze of wires here. And then get pushed to the stack through this mechanism right here. The last 2 remaining registers we can output to are the GPU point register, which is right here. And then this gets pushed to the GPU's point interface, which is in pink right here. And then also to the GPU granular system, or the GPU granular register, which is gated through here. Now, the only peripheral that we really haven't covered is the plotter here, and so I would like to talk about that now because there's a couple of components that come together that allow us to make good use of the plotter. So for the plotter peripheral, there are two major use cases. One of them is doing point operations, and then the second one is doing batch operations, and or you can call them the GPU granular system, as it was called in the Redstone Computer 4.0. And so the easiest one to talk about first are the point operations. So when you want to do a point operation on the GPU or the plotter, so that's basically drawing a point or erasing a point, you have to do a few things. First of all, you have to encode the coordinate that you want to draw on the screen into a single coordinate byte. So if we remember, we had an opcode to encode two 1-byte numbers into a single 1-byte coordinate, and that's the GPU encode opcode right here. And then once you have that encoded point, you need to write that encoded point to the GPU point register, which we just discussed, which is right here. And once you have that point written to the GPU point register, then you issue your command. So you will either be issuing a GPU draw command or a GPU erase command, and you do that via the GPU draw or GPU erase opcodes right here. And then after you issue that command, at the end of that clock cycle, you should have a point drawn or erased on the screen as appropriate. And so to wrap up, for GPU point operations, it takes 3 instructions to take 2 numbers, encode them into a point, and draw them on the screen here. Now, if you had to draw a lot of points on the screen or an advanced pattern on the screen, such as a checkerboard, then you should probably use the plotter batch mode instead, which is the GPU granular mode. And so like I mentioned earlier on, this GPU granular mode allows you to write large amounts of data to the screen at once instead of issuing many write or erase commands individually. To summarize how it works, you can specify 2 bytes of image data for an entire row on the screen for pixels that you want set or not set. And then for that single band of pixel data you define, you can pick which rows on the y-axis of the plotter you want to draw that on. Since this is a 15 by 15 screen in resolution, you need 2 bytes to specify the column data, and then you need another 2 bytes to specify which rows to apply that column data to. For a more concrete explanation of this system, I will link a video that I created that describes this in a little more detail. So to write these 4 bytes of data to the GPU granular system, we use the GPU granular peripheral, which is located at the very bottom of the peripheral stack here from the main output bus, which is right here. And the way this works is that the GPU granular register is a 4-byte register that we write to 1 byte at a time with an offset. So we have 2 registers here, or 4, and perhaps for 4 bytes, we have 1 byte of register here, another 1 byte register here, a third 1 byte register right here, and then a fourth 1 byte register right here. And these are all the control lines, the write lines for the registers. And so what will happen is that when you write for the first time, you will write to the first register right here. And then the second time you write to this location, you will actually write to the next register over. So you'll have a 1 byte offset. The next time you write, you will write 1 byte with a 2 byte offset. And then the fourth and final time you write, you will write to this register right here. So you are writing 4 bytes of data over 4 instructions to this 4-byte register, in effect. And then once you've written 4 bytes of data to the GPU granular registers via that GPU granular location as an output peripheral, then you issue a GPU granular unit command via this opcode right here with an instruction. And what that will do is it will instruct the plotter to read the data in the 4 registers that you just wrote to, or I guess the single 4-byte register, and then update the entire screen in a single command to reflect the data that's in those registers. And so the way we transfer data over to these registers is different compared to the Redstone Computer 4.0, because in that computer there was a gigantic dark gray bus, I might put a picture up of it now, effectively allowed you to write all of that data in a single clock or in a single instruction. The big downside to that, though, even though it took 1 instruction versus 5, is that we had to add an extra, at minimum, an extra 32 bits of data to the instruction word. And that is why the Redstone Computer 4.0 had such a wide instruction word, was to accommodate for those 32 bits of GPU granular data. And so I thought that was a fair compromise for this computer versus the other one, because for the demo checkerboard program, it would take, for the Redstone Computer 4.0, I believe 2 cycles to draw that checkerboard. For this computer, I believe it's 10, because you have to draw the checkerboard in 2 stages. And each stage here takes 5 instructions, 4 to copy the data over, and then 1 to issue the command to update the screen. If you didn't have this GPU granular system to write large amounts of data to the GPU at once, however, you would need a little more than 100 individual GPU point commands to draw each one of those points individually, and that would take quite a long time compared to either one of these options with the GPU granular system. And so with that explanation, that actually completes the breakdown of the computer as a whole here. And so to summarize, we have covered how a single core operates in this computer, because each, the entire computer has 4 independent compute units. We've gone over how all of the instructions are created, how they're composed, all the constituent pieces, how they all work together, the various architectural pieces of how the core is designed with the ALU. We discussed the system memory here, the RAM, and how the main input bus and main output bus connect to the 4 cores of the computer together, as well as all of the peripherals and other locations that are connected to the computer that we can read or write to, or both. And with that explanation, we also talked about the GPU, how that works, or the plotter, and how all of the pieces of the computer come together to create the full experience of the Redstone Computer 5.0. All right, so that is the end of this video. Thank you so much for watching, and hopefully that explanation was, you guys were able to follow that explanation. If not, feel free to post some comments and I'll try to clarify some things. I know some of this can be a little technical. It even is for me, even though I made this a few years ago. Thank you so much for watching, guys, and until next time, see you later. Bye-bye.